Hello, Math 201. We will be beginning a new chapter, chapter 5, which is about the other major concept in calculus, integration. And so today's section, we're going to talk about where the idea of integration comes from. And so the idea is, so from last time we learned how to actually, without knowing it, we're actually going to show how the area under the curve, which is a very important thing that we want, and I'll show you why it's important, actually is going to be calculated by the thing we talked about last time, which is the antiderivative. And so this antiderivative will somehow be related to the area under the curve. And so the picture is kind of this. You have a function, you can take its derivative, and that's kind of this like algebraic thing. And geometrically, what it represents is it's the slope of the tangent line, which is an important quantity we want to know. If we want to know how something's changing, then we need to find its derivative. The other kind of thing is we can go the opposite direction. We could take the indefinite integral or the antiderivative, but what does that represent geometrically? That's the question. And so that's where we're going to go. And so it's going to be spoiler. It's going to be the area under the curve. It's going to represent the area under the curve. And so we're going to talk about why area under the curve is important. And so first, how do you calculate area under a curve? And so if a function is just a constant, right? If you have a constant function, so it's going at a constant, then the area under the curve, we can just use geometry, right? Just use geometry. It's the area of this rectangle. And the area of this rectangle is just the height times the length, which is c times a. But what about if f of x is not constant? So let's say we want to calculate from to this point A, and we have this area capital A. How would we figure out what that area is? We can't really use geometry because it's kind of all squiggly and stuff, but we can approximate it using rectangles. So for instance, I could say, well, that's a pretty close rectangle. And then maybe this is a pretty good rectangle, and I break it up into kind of that. And that's one way I could approximate. And then so I could approximate what the area of those two rectangles are, and that would kind of approximate it. Or I could do, maybe using blue, I could use that height and do that rectangle, and maybe that height and do that rectangle, and that would be a way. And so the idea is that we can approximate, we can approximate the area under the curve using rectangles. And so let's do an example with velocity. And so remember from physics that displacement is the final point minus the initial point. It is the net distance traveled, right? So it doesn't take into account like if you traveled forwards and backwards and forwards. It's just saying, where did you start? Where did you end? And so it's not the total distance traveled, it's the total net distance traveled. And the way you generally calculate it is it's just rate times time. It's how fast you're going times how long you're going if the rate is constant, right? So here's an example. If we're going 60 minutes per hour, or sorry, 60 miles per hour, and we travel for 2 hours, how long did we go? How far did we travel? Well, it's just going to be the rate, which is 60, times the distance, which is 2. And so the area is just the displacement. It's 120 miles, right? Elapsed time, and then multiplied by the velocity. So it's rate times time. And so the area under the curve actually represents the total displacement, or how far we traveled. So the area under a rate curve, so displacement is just area under velocity curve. And so the area under a curve is actually a very important quantity. So if we have a velocity curve, the area under that curve is actually the total displacement. And so, but velocities in general are not constant, right? They're not these nice constant functions. So how can we actually find the displacement of like a messed up velocity function? We can actually use rectangles to approximate it. And so let's do that. So let's say that an object has this velocity function, t squared, between t equals 0 and 8, and it's going t squared meters per second. So at t equals 0, it's going 0 meters per second. At 8 seconds, it's going 64 meters per second. And so it's really kind of increasing its speed. We want to approximate how far it traveled, its displacement in that interval, by chopping it up into n subintervals of equal length. We're going to approximate the velocity on each and then add them up. And so I'm going to just do it really quick geometrically, and then I'll show you algebraically. So part A, we're going to do with 2 subintervals. So if we break this up into 2 subintervals, there's one interval, there's the other. And then we're going to pick the middle point to be our constant velocity. So our assumption is that in these 4 seconds, On average, we're going about 2 meters per second, which is not a bad assumption, but it's an assumption nonetheless. And then on the next 4, we're going to pick the midpoint, which is the velocity at 6 seconds, which is about 36. And so we're going to say on this interval, he's going 4 meters per second. On this interval, he's going 36. And so if you're going 4 meters per second for 4 seconds, that will be 16. And then if you're going 36 for 4, it's some number. And you add those two together, and then that would be an approximation of how far we traveled. But what if we broke it up into 4 subintervals? So between 0 and 2, 2 and 4, 4 and 6, and 6 and 8, we will pick the midpoints again. And so this will be v of 1, the velocity at 1, v of 3, v of 5, and v of 7. And then we can break it up into 8 intervals. And so we'd pick the midpoints of these. And so I'll just pick one at random. So this one is going to be v of 5.5. And so the idea is that those are the heights of our rectangles, and the widths of our rectangles are all the same. And so we just add up the area of these rectangles, and that will approximate the area under the curve. And so algebraically, what that looks like is the height of our rectangle, v of 2 times the width, plus the height of the other rectangle times the width. But our function is just t squared. So that's 2 squared times 4 plus 6 squared times 4, which is 160 meters. So in this one, we approximate it to be 160 meters. In the other one, because the width is always the same, I can actually just pull the width out and then just add up all the heights. And so v1 plus v3, v of 5, v of 7, which is 1 squared plus 3 squared plus 5 squared plus 7 squared. And so that gives us 168 when you do that one. And so this one gives us a slightly bigger approximation. And then the next approximation is if we do v8. And so that's going to be all the midpoints. So 0.5, 1.5, all the way till we get to 7.5. Those are all those heights. And then times the width of 1. And that gives us 170. And so we notice that they're getting bigger as we chop it up into more subintervals. So that means that they're kind of under approximations, most likely, because we're getting bigger and bigger. And then here's a picture of what happens as you get really the number of subintervals all the way to 64. It gets to 176.565. And so it looks like it's approximating really close. The actual answer is 8 cubed over 3. And we're going to learn how to do this in section 5.3. This is going to be the fundamental theorem of calculus. So you can just ignore this for now. But the idea is that as n gets larger, the approximation gets better, right? That's a pretty dang good approximation when we get to 64. It looks really close. And the idea is that as n goes to infinity, it's no longer an approximation, it's now exact. And so that's going to be the key idea on how we calculate this exact area. The exact area is going to be by taking this approximation and going in this limiting process to infinity. And so that's for a velocity function, but there's nothing special about a velocity function. For any function f of x, we can do the same song and dance. And the idea is that you take your interval. If you want to know what this area R is, you take your interval, your x interval, and you break it up into n equal subintervals. So x0, x1, x1, x2, all the way to xn. So that's the first subinterval, second subinterval, nth subinterval. And so here's kind of a picture of that. Each one is going to have a width of delta x. And the way you calculate what that width is just the endpoint b minus the starting point a divided by the number of subintervals. That will be the width of our rectangle. So the width of all these guys are b minus a over n. They all have the same width. And then you're going to pick generally some point in the interval, and that will be the height you're going to use for the rectangle. And then you make a bunch of rectangles and you add up all the area. And so this is what's called a regular partition, by the way, where we break it up into equal lengths. And so if you have a closed interval and you break it up into equal partitions, each of length b minus a over n, a is x0, b is xn. The endpoints are all the kind of points in between. The way that you get the kth point, x sub k, is you start at a and you move k intervals over. And so this formula works for any k between 0 and n, right? Because if you plug in 0, you'll get a. If you plug in n, you'll add n times delta x, which is b minus a, and then a plus b minus a is b. And so it works. And so this is the general formula for how you get x of k. So that's how you get the kth endpoint of the interval if you break it up into a regular partition. And then we're going to use this notation x of k star. And what that means is at some point in the kth subinterval, which is k minus 1 to k. Because remember, the first subinterval starts from 0 to 1, and the nth one is n minus 1 to n. So x sub k star is a point in the kth interval. So this is the kth interval, subinterval, I guess, subinterval. And then you can take the function value at that point, and that's the height of the kth rectangle. And so here's the picture. So you break up into these n subintervals, and then you pick some value in that subinterval to be the height. And so in general, I mean, you could pick any height, it doesn't matter. But if you want to be formulaic, you should probably pick the same one for each interval, right? So we could pick the right endpoint for all of them. This one, it's picking a random one for all of them. So the x sub k star in general can be any point in the subinterval. But if we want to do a formulaic way, we would pick like the right endpoint, the left endpoint, or maybe the midpoint. And so that's what we're going to talk about next. So that's a Riemann sum. So this idea of approximating the area under a curve by breaking it up into subintervals and then adding the area of these rectangles, that is what's called a Riemann sum. So this is Riemann, he's German. So it's not Riemann, it's a Riemann sum. And the idea is this, that if you have a function on a closed interval and you divide it into n subintervals of equal length, and you pick any point in the kth subinterval, then summing up the area of those rectangles is the Riemann sum, and it's an approximation. It's a left Riemann sum if you pick the point to be the left endpoint of our interval. It's a right Riemann sum if you pick the thing to be the right endpoint, and it's a midpoint Riemann sum if you pick the midpoint of our subinterval. And so here's pictures of that. So left endpoint is the height of our rectangle, right? For all of these rectangles, the left endpoint is our height. For a right Riemann sum, we pick the right endpoint for all of them. And then for a midpoint, we pick the midpoint of our rectangles, or the midpoint of our subintervals to be the height. And so the left, right, and midpoint Riemann sums. We're going to use this notation. Ln is going to be left Riemann sum with n rectangles. Ln, and so the formula for that is b minus a over n, because that's the width. And then we're picking the left endpoints, right? And so it's the left endpoint will be x sub 0, x sub 1, all the way to x sub n minus 1, because those are the left endpoints of our thing. The right Riemann sum is going to have this formula, same width, and we're picking the right endpoint. So it's the function value of x1, x2, xn. So you'll notice that this one starts at x0, this one starts at x1, this one ends at n minus 1, this one ends at n, because we're picking the left endpoints, this one we're picking the right endpoints. To do the midpoint, it looks really gross, but this is the formula. It's the midpoint of the intervals, or what you're plugging in to all those. And we're going to use the formula. We're going to call it m sub n, r sub n, and then l sub n. So let's do an example. Let's do the left and right Riemann sums for the following function, 3 times the square root of x between 4 and 16. We're going to approximate the area of R using the left Riemann sum with n subintervals. So our starting point is 4, our endpoint is 16. If n is 6, then our delta x is 16 minus 4 over 6, which is 2. And so what are the endpoints of our interval? They're going to be 4, 6, 8, 10, 12, 14, 16. Those are going to be the endpoints of our intervals, but we're picking the left endpoints. So we want 2, which is our width, times f of all of those ones. We're going to plug in the left endpoint, so not that one. And so that's why it's f of 4, f of 6, f of 8, f of 10, f of 12, f of 14. You plug all of those into the function 3 times square root of x, and we get that value. And so then it's 2, and then you just add all those up. And so if this was an exam, this would be the final answer. That would be totally fine. But we have calculators, and so it's approximately that. So that's what the left endpoint is. And then this is a picture of it. So 4, 6, 8, 10, 12, 14, 16, and we've picked the left endpoints to be the heights. And then we find these areas by adding up all the heights and then multiplying by the width, and we get that. Doing R6 is very similar, but instead of picking, we're not going to pick that one. We're going to pick those guys, that guy, that guy, that guy, that guy. So we start at 6 and then go to 16. And so it's 2 times 3 times square root of 6 all the way to here, and you get 117. And so you'll notice that these are very different. This one is an under approximation, right? 105. And then this one's going to be an over approximation because they're all over it. When we pick the right endpoints, it's an over approximation. And then, so because the reason is because this function is increasing. And so when we pick the right endpoint, it will be above, right? So if we have an increasing function, a right endpoint will be an over approximation, and a left endpoint will always be an under approximation. And so R6 is an over approximation, right? And then L6 is an under approximation. But if it was a decreasing function, it would be the opposite. If it was a decreasing function, we pick the left endpoint, we would be over approximating, and the right endpoints would be under approximating. So it's because it's an increasing function. All right. Let's talk about sigma notation. So a reminder what sigma notation is. So you have a sigma and you have an index. K equals, generally we start at 1 or 0, it doesn't really matter. But let's say we start at 0 to n, so of, I don't know, k plus 2. So what is that? That means, and let me make this actually a real number so I can show you what it looks like. 4. So what is that? That means you plug in 0 for k for the first term. So this will be 0 plus 2, and then plus, and then you plug in 1 plus 2 plus 2 plus 2 plus 3 plus 2 plus 4 plus 2. So that's what it is. So sigma notation is just a compact way to rewrite a long sum of things. And so for instance, the sum from k equals 1 to n of k is just 1 plus 2 plus dot 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 to n. To 99 is 1 plus 2 plus 3 to 99 was that. The sum from 0 to 3 of k squared is, you have that, or something like this. And it follows some really nice rules. So if you have, so you'll notice that the index right here is k, and that matches the formula that's here, right? These are in terms of k. And that if you have a constant, you can pull the constant out and then just do it. And the reason is because you add a bunch of things and then you multiply by c, you're multiplying each one by c. So it's really just a distributive property. And then the sum rule, if you have two things with k being added, you can split up sigma over sums. And that's because you can just regroup these, right? If you have a1 plus b1 plus a2 plus b2 all the way plus an plus bn, you just rewrite them. So a1 plus a2 plus an, b1 plus b2 plus bn. And so that's why you can do the additional. And then generally this is how we should think about a sigma notation from k equals 1 to n. It's a1, a2, all the way to an, where ak is a formula involving k. And so these are really important ones that or formulas that you'll need for basic ones. And so the sum of c, where c is a constant, is just c times n, because it will be c plus c plus c plus c plus n times. And so n times. And so that's why it's c times n. The sum from k equals 1 to n of k is this formula. I won't prove where that comes from. And then k squared ends up being that formula and that formula. And so this gives you a way to actually calculate this sum without actually doing the sum. It just only depends on what n is. And so why sigma notation is nice is because it gives us a way to write Riemann sums in a very compact way. So remember, a Riemann sum looks like this, but using sigma notation, that is just this. So for k equals 1 to n, f of x of k star delta x. And so depending on what x of k star is, we can write the Riemann sum using sigma notation in very different simple ways. So for a left Riemann sum, this is the formula, but what x of k star is just a plus k minus 1 delta x. For a right Riemann sum, they're all the same. These are always going to be the Riemann sums, but it's just changing what x of k star is. For a right Riemann sum, x of k star is a plus k delta x. And for a midpoint one, it's a plus k minus 1/2 delta x. So let's do one final example. So let's calculate the Riemann sum for this function. We want to approximate this area from 0 to 2 of x cubed plus 1, and we want to do it with 50 subintervals. And so obviously we're going to have to use a calculator to figure out what this exactly is, but we can set it up really nicely. So by this formula up here, L50 is just the sum from k equals 1 to 50, and it's f of x sub k star times delta x. And so our goal is to figure out what all those things are. Well, delta x, remember, is b minus a over n. So it's 2 minus 0 over 50, which is 1 over 25. That's what delta x is. X sub k star, because it's the left endpoint, is a plus k minus 1 times delta x. And so a is 0 plus k minus 1 times delta x, which is 1 over 25. And so this is going to be equal to the sum of k equals 1 to 50. And now what is f? F is x cubed plus 1. And so what is f of x k star? Well, that's going to be you just plug in this thing right here into the function. And so it's going to be k minus 1 over 25 cubed and then plus 1. So that's what f of x k star is. And so let's plug in all those pieces. So I'm going to plug this in for that. And I'm going to plug in this piece for that. And what do we get? We get k minus 1 cubed over 25. Sorry, that whole thing is cubed, not just the top part. That, because that is what x of k star is. So that thing cubed plus 1, and then that whole thing, because that's what f of x k star is, and then that times delta x, which is 1 over 25. And so we could plug that in and figure out what that is. And so, yeah, that's going to be pretty gross. So how would we plug this into a calculator? It's a great question. So this one actually is pretty gross, and I won't simplify this any further. We'll just leave it like this, and this will be a sufficient answer, just because, I mean, actually trying to figure out what this is disgusting. If I was trying to do this on a homework, I would just plug this into a Riemann sum calculator. So just plug in to Riemann sum calculator, Riemann sum calculator. That's totally fine for the homework. And then for the quiz and test, I won't have anything that difficult. R50, on the other hand, is one that we can do because it's going to be a much nicer formula. And so R50 is still the sum from k equals 1 to 50, and it's still f of x sub k star, delta x. But in this case, delta x is still 1 over 25. But x sub k star is much nicer now. It's just k times delta x, which is k over 25. So that's what x sub k star is. And so f of x sub k star is really nice. It's just k cubed over 25 cubed plus 1. And so this is going to be the sum from k equals 1 to 50. And then it'll be k cubed over 25 cubed plus 1 times 1 over 25. And then what we can do is we can break this up using sigma rules. And so distributing this 1 over 25 to both of these gives me a 1 k cubed over 25 to the 4th, and then plus 1 over 25. K equals 1 to 50. And then using, that's to the 4th power. I should probably make that more obvious. 25 to the 4th power. And then breaking this up into two sums and using our sum rules. This, oh, that's a 4. 25th to the 4 sum from k equals 1 to 50. And then this will become k cubed. And then plus 1 over 25 times the sum from k equals 1 to 50 of 1. Now these two guys, I can use the formulas up here. I should probably copy these. Copy. I'll use those formulas to get what these guys are. Copy. So this formula right here, I can plug in right here. And then this formula right here, I can plug in right there. And so this is going to equal 1 over 25 to the 4th, and then times So the sum from k equals 1 to n of k cubed, so 1 to 50 of k cubed is 50 squared plus, and then 51 squared. So it'll be 50 squared times 51 squared over 4, and then plus 1 over 25 times, and then this will just be 50 times 50. And so that's the final answer, which I have no idea what that is, but that gives us an approximation of the area. And so I think it's roughly, let me see. So plugging this into a calculator, we get that this is actually 6.1616. And so that is one way. And so this kind of using these formulas to kind of simplify sigma things, that formula and that formula, that's going to foreshadow what we're going to do in the next section. And then finally, I'll also show what the formula looks for M50, even though I won't calculate it. So for M50, again, the formula is K equals 1 to 50, and it's F of X sub K star times delta X. Delta X is the same thing. It's still going to be 1 over 25. And now this case, X sub K star is going to be, for the midpoint, it's A plus K minus a half times delta X. And so in this case, it will be 0 plus K minus 1/2, and then times delta X, 1 over 25. And so plugging that in, we get that this is equal to the sum from K equals 1 to 50. And then it'll be K minus 1/2 to the third over 25 to the third plus 1, and then times 1 over 25. And so that's the answer. Okay, that should get you through everything for 5.1. Take care.